Okay, so tomorrow is the first test. So let's talk about that first. Exam 1 is on all the material up through, I guess, this example problem that we're going to start class with today, but basically up through yesterday. And so the for the problems, for the exam itself, the material that you're responsible for is understanding how to do problems like the vector review, free body diagrams for particle statics, and then the particle statics problems. And so if you're comfortable with all these problems, I would say try to do each of these problems at least twice. Understand why you're making the decisions you're making. You'll be in good shape for the test tomorrow. And then lecture quiz 1, you can just think of that as sort of part of the exam. But this is the part where the questions are not going to be problem solving. They're just going to be on stuff that I said, just to make sure that you're going through the notes carefully enough. So it's like short answer. So I would, like an example would be like, what's the subscript notation version of Newton's third law or something? Okay. And you'd have to come up with that, something along the lines of FAB is equal to negative FBA, So let's say that this is up through yesterday. And I won't write the exam meaning it to be a 2-hour exam. So, most people I think will leave early. There's nothing going on after the exam, so feel free to leave after you're done. Anybody have any questions about the exam or the quiz? Yep.
Do you post grades in D2L or how do you?
Yeah, they'll all be on D2L. It'll definitely all be graded by Monday, and it'll all be on D2L by then. And so I'll keep as I grade stuff, it'll keep getting entered into so you'll sort of know where you stand the whole time. Any other questions? Okay. I'm going to do one more example problem that's relevant to the exam tomorrow. And then if you'd like, I'd be happy to answer as many questions as you have about the practice problems that are going to be on the exam tomorrow. And then if you don't have any or we run out of those, then I'm going to move on to the next topic, which is rigid bodies. Okay, so let's go through this example problem first. So resting on a flat floor is a 10 kilogram box with a 5 kilogram box on top of it. And a cable is connected to the 5 kilogram box that goes over a pulley. And connected to the other end of the cable is a 2 kilogram box. And then in addition to that, there's a horizontal force on the 10 kilogram box of 25 newtons. And say that the system's in equilibrium. What's the force vector applied to the 10 kilogram box by the 5 kilogram box. Okay, so first of all, is there a way to know whether there's friction or not without me mentioning it? Well, I guess and you need to know this angle. This is 45 degrees. If you could calculate the horizontal component of this tension force, if it's anything other than 25 newtons, then you know there's a net horizontal force and this thing will slide. For our purposes, let's just say, and either way, even if that is 25 newtons, there has to be friction between these two if this is going to be in equilibrium. Okay, so basically I'm going to look at this and say there's horizontal forces. I'm not going to go through the effort of figuring out what they are, but there are horizontal forces, so I'm going to assume that there's friction. Okay. And we can use Newton's second law for a few things. We could do these two boxes together as an isolated object. We could do the 5 kilogram box as an isolated object, the 10 isolated, and the 2 isolated. So we have all those options, and we're just trying to use the ones that help us solve this problem. So you wouldn't have to do this to solve a problem on a test, but I'm going to start out by drawing all of these free body diagrams and just seeing where the variables come up that we're trying to solve for. Okay. All right, so free body diagram of the 2 kilogram. So there's the 2 kilogram box. Here's, this is the thing that Ben mentioned yesterday, and I said, sometimes it helps people to include just a little bit of the cable when a cable's attached to an object, and then the force comes out of that little cable stump. So we have an upward force. We don't know what it is. We'll call it T. And then a downward force of 2 kilograms times 9.81. Are there any other forces acting on the 2 kilogram box? No, I mean, you can think of it as, so there's definitely going to be weight that's in there, and then you just go around looking for contact with the boundary, and the only place there's contact is in there. Okay, so this one doesn't have, the force vector that we want is the force on 10 by 5, right? We want F10, 5. That doesn't appear here. So we know we at least can't just solve this one and be done. But it turns out this one's going to come in handy. Then free body diagram of the 5 kilogram box. There's the weight of 49.05. And where else are there forces? Yep, that tension going this way. That's right. And you can break it up into friction or normal force. I was talking about this to a couple of people after class yesterday. For our purposes, I mean, the only reason to break up the contact force between these boxes into a normal force and a friction force is if you know the coefficient of friction. That's not something that we're going to be dealing with in these, so I'm just going to call that, so it doesn't help to say this is the friction, this is the normal force. They combine to create a force vector, and I'm just going to call that the force on the 5 by the 10. Then a free body diagram of the 10 kilogram box. What forces are acting on this one? Yeah, there's the 25. So I'm going to do the weight first, I guess. 98.1. And then there's that 25 newtons this way. And what else? So we're just going around the boundary looking for contact. There's contact. Yep. And so that is the force on 10 by 5. Newton's third law says that's negative F510. That's something that, so if we were going to use both of these two, we would want to express this in as few variables as possible. This force vector F10, 5, that's a different force than this one. That's a different variable. And so it would be in our interest to remember that this is the same thing as negative F510. And then instead of adding 2 more variables, we use the same ones we had over here. Okay. It turns out in this problem, that's not going to come up. And then down here, there's contact with the ground. So that's the force on the 10 by the ground. And then another thing that, you might expect to, that might, often thinking this way could be useful, is to lump the 5 and the 10 together. So for this one, we have a weight. The mass is 15 kilograms. So the weight is 147.15. We have the tension. We have the 25 newtons. What about the contact force between these two? That's not in there because it's not on the boundary. So those are internal loads. And then, yep, down here, this is the same force as this one. So this is the force on 10 by the ground. Okay, so which of these are going to help us? There's really, I guess, well, there's probably several ways to go, but the fastest way to go is we can use Newton's second law for the 2 kilogram box to figure out the tension, and then use that tension in the Newton's second law for the 5 kilogram box to find the force on 5 by 10. That's not what we want. We want the force on 10 by 5. But remember, Newton's third law says that those are equivalent. All you do is switch the signs, and then you have the one you want. Any questions about these? By the way, I think I raised this question, but I don't think I ever brought it up last time. Newton's second law says add up all the forces on an object, and that sum has to be equal to the mass times the acceleration, or 0 in our case. And we made the, lucky, necessary leap of saying we're only dealing with the external forces. So what is it about the internal forces that lets us get rid of them all? I mentioned last time that the answer is Newton's third law. And the reason is that every force, every internal force, every force on one part of this by another part of it is in a pair. So like if this atom applies a force F to this one, then the other one applies a force negative F to it. And so all those internal forces appear in pairs that cancel each other out. The only forces on our chosen object that don't cancel out are the ones where at the boundary, this says there's a force coming from outside, and the outside says there's a force coming out to me too, and we say we don't care about you though, because you're where our boundary is, So you cut it. That's where you make the cut that pair doesn't cancel, and that's why the only things that matter to us are the forces happening on the outside boundary. That's awesome. Okay, but I mean, it's lucky because if we had to, every time we use Newton's second law, we had to include a sum of a billion forces, that would be a problem. Okay, so Newton's second law for the 2 kilogram object. We can use any coordinate system we want. I'm going to just use a standard coordinate system. There's no reason to rotate it. So we have an upward force with a magnitude T. One way you could think of that, if you wanted to, is you could think of this the same way like when we use cosine and sine. This is a vector whose unit vector, whose direction is defined by cosine of 90, sine of 90. So a unit vector of 0, 1 multiplied by a magnitude of t. Okay, so this is 0t. And then this one's in the negative y direction. So 0, negative 19.62. And those are equal to 0, 0. So that gives you 2 equations. The first one doesn't help. It just says 0 is equal to 0. But the second one says t minus 19.62 is equal to 0. So t is equal to 19.62. Okay, so now we can take this extra information and put it in here. You don't have to draw a new free body diagram for this, but I'm going to just do that extra step to try to be really clear on this. So this is our free body diagram. So now instead of t, we know that this value is 19.62. This angle is 45 degrees, so it's counterclockwise 45 degrees from the positive x-axis to get to this vector. If you think about putting the tail of this vector at like an origin of a coordinate system, right? This is 45 degrees. So this vector is 19.62 times cosine of 45, sine of 45. Can someone multiply that out? So that's 19.62 times, these are both 0.7071. Okay. So 13.87, 13.87. If you calculated the magnitude of this vector, what would it be? Do it in your head. This squared plus this squared, square root. Yeah, 19.62, yeah, right. Okay, so Newton's second law says 13.87 plus 0, negative 49.05 plus F 510 X and Y components is equal to zeros. And so you get the force on 5 by 10 is equal to negative 13.87, positive 35.18. But that's not what the question asked for, so now you have to use Newton's third law. And that tells us that the force on 10 by 5 is equal to positive 13.87, negative 35.18. These are Newtons. Yep.
On the test, do we have to put like Newton's third law?
No, you don't have to do any of that. One thing I would recommend is, because I've seen it, a lot of people like sort of skip this step and just get turned backwards. I'm not going to mark anyone wrong for not doing this, but I think it's a good idea to write out Newton's second law and then eventually the rotational version in this form, where you have all the forces on the left side and the zeros on the right side, instead of like already starting to rearrange it in your head to solve for variables. Do you know what I mean? I would recommend that, but as far as like the procedure, really all I'm saying that you have to do is draw the free body diagram. Okay, like anything else that works for you to get to the solution is okay with me. Yep.
For this problem, if we don't have a 25 force to the left, so does that mean we don't have friction?
That 25 Newton force was acting on the 10 kilogram object. So it turns out that, I mean, you can imagine that some of these kind of things, they get complicated if these are dynamics problems, but as statics problems, having all these forces, like that 25 Newton force would come into the problem in a way if this was a dynamics problem. But like, imagine everything's static, right? Nothing's moving. So imagine that instead of this being a block that can slide along the floor, imagine that's just cement that's cemented to the ground, you know, like it's fixed to the ground. Then obviously intuitively, it doesn't matter whether you're applying 25. If you're just trying to figure out the force that's applied to the 5 kilogram box, it doesn't matter whether someone's pushing on that piece of concrete or not. And so, yeah, in this one, that 25 Newton force doesn't affect the answer.
So if we take out a 25, we still have the F on 10 by ground.
Well, you wouldn't take it out. I mean, it wouldn't, the free body diagram of the 10 kilogram box would not be correct without that 25. But we were just able to solve this problem without looking at the free body diagram for the 10 kilogram. And that's why the 25 didn't come into it. But even, so.
I think what he's saying is that because
Mhm.
because of the 25 force,
Yeah.
we were able to assume that there was friction without
Oh, I see.
another force component.
Oh, I see what you mean.
That there's friction.
I see what you mean. Well, the tension here is applying a horizontal component of the force on the 5 kilogram box. And so there has to be friction between the 5 and the 10. Between the 10 and the ground, it turned out that didn't even come into the problem, whether there was friction or not. Any other questions about that one? Are there any practice problems that anyone finds confusing or anything? I'd be happy to answer questions about that kind of stuff before we go on to the next topic.
Could you do the one that's the block on the incline? I was just confused how you got some of your angles.
Okay, yeah. Does anyone have those? Have those printed out? Thanks. Oh. So the one with a block on an incline, did I use angles in my solution? Oh, then I was just, okay, yeah, sorry. I guess I was just pretending at that point that those were given in the problem. Like those would have to be given to come up with angles.
Yeah, it was good.
It was given? Oh, okay.
Yeah, you gave it.
Oh, okay, okay.
It was just somehow you came up with like a -70 and
Oh, okay.
-20.
Yes. Okay, so that has to do with, remember I mentioned when we were talking about unit vectors, when you know the angles, I was talking about that idea where you start out at the x-axis and then rotate this way to get here, and then maybe rotate some angle this way to get here, like for these things where you have to do it in a bunch of steps. And so that's what we're going to do for this one. Okay, so we have an incline with an angle of 20 degrees. And the block is 20 kilograms. And there's a horizontal force pushing this way, 50 newtons. This is number 3C. Okay, so a free body diagram. Well, I guess, so we're just doing all of 3, I suppose. Okay, so there's a weight of 196.2. We're assuming that there's friction. So that means there's a full force vector acting between the block and the incline. So that's the force on the block by the incline. And then there's a horizontal force of 50 newtons. And you can see, since we didn't break this up into a normal force and a friction force, we're going to do Newton's second law without that angle even coming into it, right? So Newton's second law says F BIX, F BIY plus 0, negative 196.2 plus negative 50, 0 is equal to zeros. And so solve for FBI, that's 50, 196.2. Okay, so there's the force vector applied to the block by the incline, okay? And so the force on the incline by the block, you just use Newton's third law. But now I think the question you're asking is about how to figure out how to break this up into a normal force and a friction force. Well, basically what we want to do, if you, so let me just draw this so you can sort of visualize what this vector looks like. It has an x component of 50 and basically a y component of 200. So it looks something like this, right? And the incline is like this, 20 degrees, so something like that, right? And what this question is asking is for you to break this vector up into a component that's perpendicular to the incline, where this is 90 degrees, and a component that's parallel to the incline, like that, okay? This is going to be the friction force, and this is going to be the normal force. And so what we have to do is come up with a unit vector in the direction of n, come up with a unit vector in the direction of ff, and then just take the dot product. Anytime, so if you take the dot product of this vector, 50, 196.2, with a unit vector in the direction of this normal, it's going to give you the projection of this onto that normal line, which is what we want. Okay, so
So is that angle like right in there? Is that the 20 degrees?
this is 20 degrees.
So then by similar triangles, is that other angle instead of your unit vector?
No, because it is not necessarily, because this is not at, okay, so let's go through how to think about how to, like, our goal is to come up with we want to find unit vectors in the directions of that normal and that force of friction.
But if the projection is on the unit vector, I mean, then it could only be, then it could be the full projection.
It is. So,
Vector multiplied by it.
so think about if you have a vector 0, 50, okay? So the vector looks like this. What's its projection going to be onto the y-axis? That's sort of like a redundant question or whatever, but what's the projection of this vector going to be onto the vertical axis? It's going to be 50, right? So what do you have to dot this with to get an answer of 50 for the projection? You have to dot this with a unit vector in that direction. If you dot it with anything besides a unit vector, you're not getting a projection. You're getting a projection times something else.
In that case, is it, because the 0 is a 0, 50 would matter. The second one is the unit vector. It would be 1, 1, and you still be 50.
Yeah, that's true in this case. But in general, if you don't know that one of the components is going to be 0, what you want to dot something with to give you a projection is a unit vector. Okay. How about this? Okay, so say that you have say that you have a vector, this angle is 45 degrees, say the length of this is 100, okay? Then in this coordinate system, the components of this vector would be 70.71, 70.71, okay? What would you have to dot this vector by? Well, let me think of it this way. If we took a projection of this vector onto a line parallel to it, what should the answer be? Should be 100, right? And so what's a unit vector parallel to this line? It would be cosine of 45, sine of 45. So it would be this. Take that dot product and you get 50 plus 50 is 100. So if you're just trying to find a pure projection onto a line, the way you do it is dotting with a unit vector. That's all I'm trying to say there. Okay, so the next challenge, well, anybody have any more questions about that projection thing? The next challenge is coming up with unit vectors that are in these directions. Okay, so the way I'm going to do that is I'm going to figure out what angle I need to rotate from the positive x-axis to be going this way, okay? And then I'm going to figure out what angle I have to rotate from this to get to n. Those two are perpendicular, so it's just going to be a clockwise angle of 90. Anyone following me here? Okay, so yeah, first I'm going to do it for n. So first I want a unit vector in this direction, okay? I'm going to do it in 2 steps. I'm going to find the angle to here, and then I'm going to add it, well, let me say, then I'm going to go clockwise 90 degrees to get to here, okay? This and this are perpendicular, right? So if I can figure out the angle to get from the positive x-axis over to here, then I can just subtract 90 to get to this one. Subtract 90 because it's clockwise. Okay, so what's the angle? What do we know here? Yeah, that's right. So if here's our coordinate system, we're given in the problem that this angle is 20, right? So it's counterclockwise 180 minus 20, okay, to get in this direction. And now to get from, okay, so we started out here, right? I rotated 160 to get here. So now we're here, and we're at 160. And now we're going to rotate negative 90 to get here. So 160 minus 90 gives us 70. So that's where that 70 came from. So theta is equal to 160 minus 90 equals 70. And so the unit vector is cosine of 70, sine of 70, which is 0.94 and 0.342. And so then the last step is multiplying FBI, so 50, 196.2, dotted with 0.940, 0.342. What do you get if you dot those? Okay, 201.47. Okay, newtons. So is that the normal force or the friction force? That's the normal force, yep.
Are you sure you get that? It seems you have a 0.9 and a 0.3.
Yes, they do. They are switched. You're right. Thanks. So this is 0.342, 0.94. Was that still the right answer? Or?
Yeah.
Okay, yeah. Okay, so 201.47, I think it was. So that's the normal force. Okay, so now the friction force. It's more of the same, but let's go through it. So yes, right, and basically we want the angle that we had the first time. We're gonna go from the positive x-axis to the incline, so we can just use that 160 that we had before. So now we're going to find the unit vector along the incline, going this way. So theta is equal to 160. And that means the unit vector is equal to cosine of 160 sine of 160. And I think this time it should be negative 0.94 and positive 0.342. And so the friction force is 196.2 dotted with negative 0.94, positive 0.342. And what do you get for that one? What if none of you had put batteries in your calculators yet? It didn't say that on the syllabus.
20.1.
Okay, 20.12 newtons, and that's the friction force. Okay. Yes, that's right. So, and if we would have instead made our unit vector go down the incline like that, we would have gotten negative 20.2, which would have said that our guess about the direction was backwards.
So, all right. So say that one more time.
Well, so we did 160 degrees to get it going this way, but if instead we would have taken negative 20 degrees to make it this way, we would have gotten an answer of negative 20. And so if you, basically it's saying negative 20 times this unit vector, which is the same thing as positive 20 times this unit vector. So either way you get, the right answer. It's just a matter of interpreting it.
Okay, all right.
Yep.
So if we do have it negative.
Yeah, that would be perfectly
That's okay.
fine.
All right.
That was just a matter of guessing which direction the friction force would be. And if you guessed right, you get a positive. If you guess wrong, you get a negative. And it gives you the right answer either way. Okay, I want to show you something cool since we're talking about this. So this is something that's going to come up in a couple of weeks, but I'm going to introduce it now. The idea of a rotation matrix. If your vectors are expressed in coordinate system A, and you want them expressed in coordinate system B. Okay, so what you need to do is find the counterclockwise angle that aligns A with B. Okay? So for example, if this is coordinate system A, and this is coordinate system B, then how do you have to rotate A to make it line up with B? You have to rotate it this much. Okay. If B was rotated clockwise relative to A, then you'd get a negative theta answer or a 300-degree answer or something, you know. Okay, so once you have that angle theta, the rotation matrix Q is equal to cosine theta, sine theta, negative sine theta, cosine theta. And if you left multiply your vectors by the matrix Q, it gives them in the new coordinate system. It gives them in coordinate system B. So I just want to show an example of this. It applies really nicely in a problem like this. Question? Okay, so to multiply matrices to vectors, the left versus right just means I'm just saying the matrix has to be on the left of the vector instead of on the right. But so if you have a matrix A, B, C, D, and you're multiplying it to a vector E, F, you, the way this works is, you can't do what?
You can't do a 1/2 matrix.
Yeah, right. You couldn't do it. Yeah. And anyways, even if you could, the order matters in matrix multiplication. So you need to be clear on, but yes, so this is the way you want to do it. The vector on the right, the matrix on the left. The answer here is a vector that is, it's basically two different dot products. The dot product of AB with EF. So you get AE plus BF. And then the y component is CE plus DF. Okay, so like you take you first take a dot product of this vector with this vector, and then you take a dot product of this vector with this vector. What?
So it's just called leftmost?
Yes, that's right, because the matrix is on the left. Yeah, right. Okay, so let me just demonstrate this on the problem we just did. So you know from physics that if we had just, instead of using a standard coordinate system, started this problem with a coordinate system rotated like this, we would have come out naturally with the normal force, you know, with our vector broken up into a normal force and a friction force. So let's take the answer that we got, the contact force on the block by the incline, multiply it by that rotation matrix, and what we should get is a new vector with the y component giving us the normal force and the x component giving us the friction force.
Which theta do you use for 160 or the 20?
Okay, so yeah, let's think about that. So back to our problem, our original coordinate system is this. And we want to transpose these vectors into a coordinate system like this, where this angle is 20. And so that's a clockwise rotation to get from A to B. So our theta is equal to negative 20. And so our rotation matrix is negative. Our rotation matrix is cosine of negative 20, which is 0.94, sine of negative 20, which is negative 0.342, negative sine of negative 20, which is positive 0.342, and then 0.940. And now our new transposed force vector is 0.940, negative 0.342, 0.342, 0.940, multiplied by our contact force, 50, 196.2, and give me a couple seconds. Okay, so that gives us negative 20.21201.47, if my calculations are correct. I'm just remembering that from before. I didn't really do that. Okay, so I know what you're thinking. You're thinking, are you sure that makes it any easier? It doesn't seem like it. But when you have the rotation matrix programmed into your calculator, and all you have to do, and that's one of the programs that's on the sheet on D2L, and all you have to do is figure out what that angle is and enter it in, and your calculator does all the rest, then yeah, this is very fast, you know. But this rotation matrix stuff, obviously, none of that's related to the test, really, but this is something coming down the line. For one thing, it's a reason why we're using this, this 1x2 matrix version of vectors. It's so that we can multiply vectors by matrices, because that's a useful thing to do in mechanics. You know, like a lot of people were wondering why we're using this notation with the x component on top of the y component. It's so that we can do matrix multiplications. Anyone have any questions about that? You don't really, I guess I brought that up because I think it sort of helps to get a glimpse of that before the time that you're expected to really understand it. But that's coming down the line, and it's related to this problem. So, any other questions about that problem? That sort of veered away from what that problem's about, but. Any other questions about any of the other practice problems? Maybe we should get those out of the way now, then take a break and move on to the next stuff. Okay, well, let's take a 10-minute break, come back at 2:09 or so, and we'll start with the new material.